And University of Kentucky has a long tradition of electric machinery going back for about 50 years. Many, especially in the US, have learned electric machines based on the classic books by Nassar and Bolda. In more recent times, we have established the Power and Energy Institute of Kentucky, PIC, which started about 6 years ago with support from the Department of Energy. And more recently, the endowed chair, which I'm holding, has been established. And the group that I am leading within PIC at University of Kentucky is named SPARK. And this name will come across quite a few times during the presentation. I would like to take a moment to provide the acknowledgement to the colleagues that made the direct contribution to the presentation we see today. And first of all, we have Multi-Design Limited, with whom we have collaborated many times over the years. And in actual fact, Dr. Dave Stator, who is the principal with Multi-Design, is here with us today. And the company is known for being the software developer of MultiCAD and MultiLab, which has been actually used to provide all the examples that we included in the first part of the presentation. And then for the second part of the presentation, that is reflective of the work I have done with the colleagues at the Center of Applied Energy Research at University of Kentucky, which is a large organization within the university. And I should maybe say that in the US, University of Kentucky is known by simply UK. And the reason we carry the brand is because we are very proud to have the most successful basketball team of modern times. And that carries the brand of UK in the US. So we'll have two parts of the presentation. In the first one, I'll be discussing what can be achieved, what we can reach with the existing materials, and we will focus, this is the way we thought about the presentation, to focus through examples. So the examples I'll be using for the first part comes from a impressive Formula E racing car, and sets a record in terms of torque density, and we'll see the role played by innovation, played by large-scale optimization and multi-physics analysis, which will cover both electromagnetic and thermal. And then in the second part of the presentation, I'll be talking about more futuristic things, and that is the emergence of new materials, especially nanocarbon tubes and wires. And what are the better example could be than to look at concepts that will be applicable in that case for solar, planes, and cars. So let me get started here and talk a little bit introduction about the Formula E. This, the first season was started in 2014, and the work has been divided on the engineering in between various companies. And the topic we will be covering will refer to the electric machine. And what makes the application very interesting, and it is at the end of the day, it is at the very origin of making the possible record achievement we will see, is the fact that the driving cycle is well known. So there are relatively small variations in between cars and drivers as they go on the laps. And here we have a representation of the torque and the speed versus time. Now, if we look at just to set things in perspective, to understand how we position ourselves, the motor in question, the example is the A motor, which is listed the last in the table, okay? And this is by no means a competition, right, per se, but we just want to put things in perspective. And if you look at the type of machines employed by other electric or hybrid vehicles, they are different. Their torque per weight ratio is also largely different. We'll explain that what may be the case. And then if we look at the A motor and we compare it with the YASA, and we look at the values for TRW, we should not forget the fact that the rating for the machines is largely different. The YASA machine is has three times the torque of the AIM. And as we know from the theory and practice of electrical machines, typically electrical machines get naturally better as the size increases. So for a small machine, which is only 110 Newton meter, relatively small, only 9 kilograms, this is really indeed a record setting. So I would like to bring to the discussion how some of the teachings from the Formula E, which is a specialty application, can be applied to the more common industrial applications, because that will make an impact to the wider community. So if we look here in a typical pump or a constant torque application or a fan curve, one would have to investigate what happens in terms of the torque versus speed and with the efficiency, and then we compare various operating points within the operating range. If we design electrical machines for electric traction, say for an electric vehicle, the driving cycle itself is known, but nevertheless the variations from one car to another, depending on the traffic, can be largely different. So that is in a way a different challenge. But the way to approach the problem is to do optimization. And if we look here at 3 parameters, normalized energy versus normalized torque and normalized speed, we select typically a number of points that would be the most important to define an objective in terms of weighted importance. Okay, and here we have figured the most important for a typical driving cycle. Now, with modern technology, we can no longer talk about one unique optimal solution. If we optimize for multiple criteria, and the example we'll have here optimizes to reduce material cost, and at the same time to reduce the losses, the most important being the stator losses, then we end up with a family of curve. And what we represented with the small circles are all the candidate designs that have been investigated to a systematic design procedures, and they are into the thousands. And the automated design, which is inspired from computational artificial intelligence, is based on a differential evolution, will progress, and then it will reach what we see here demarked as the Pareto front. And the Pareto front has, strictly speaking, a very clear mathematical definition, meaning that any point on the Pareto front, right, for any point here, improvement in one objective can only be achieved if we allow a deterioration in another. So here we can have machines that will have lower losses and higher cost, or we may have machines that have lower cost and higher losses. If we do systematic studies like this, which I highly encourage the technical community to do, we may come across things that may contradict common teachings. For example, one common knowledge is if you want to have a good IPM machine, you have to have the saliency very high. Well, not necessarily. If both cost and efficiency are important at the same time, and if the material cost is actually more important, you may come to the conclusion that saliency in actual fact doesn't have to be that high. Also, if one does studies like this, is able to establish the influence on other parameters, such as, for instance, the fundamental power factor, and understand the natural limitations that may come with a certain technology. So I'll take a moment to go outside of the Formula E racing car and use a couple of slides that come from a different application. And this is an industrial. It is an example for a 10 horsepower, 1800 RPM machine. And what we did, we undertook the task of systematically comparing synchronous reluctance technology with synchronous reluctance permanent magnet assisted, which will mean that in one case we insert magnets, in our study ferrite magnets, within some of the flux barriers existing in the synchronous reluctance. And we established a robust model with independent variables related to the cross-sectional geometry of the two machines. And we looked at two objectives, one being to maximize the power factor and the other one to minimize badness. And those who may not be familiar with the badness, think of the goodness. And the goodness is defined as the Newton meter of shaft torque divided by the square root of watts of losses. And now that I said the entire story, I guess many would be familiar with this global index, which contains both the specific torque as well as the cooling capability of the machine. And when we run the study, we ended up with all these candidate designs and their Paretos, and we are able to see that if we would use permanent magnet synchronous reluctance assisted technology, the improvement both in power factor and in terms of goodness would be absolutely extremely significant, yes? And the numbers should speak by themselves. And if we take then a closer look at the, let's take for instance, this study was done using the same core length for all the machines. So as such, the output power for the machines, which is figured in this corner here, will be largely different in between the designs. Shown here are the limits for the synchronous reluctance. We go and show what happens in the permanent magnet synchronous reluctance assisted. So large differences, big increase in the power density. But the most important takeaway is, without making a systematic study like this, it will be very difficult to pass judgment, especially if you target multiple objectives, cost and, say, technical performance on the other hand. To complicate the problem even further, when one deals with extremely heavily loaded, electromagnetically heavy loaded machinery, it's very important to study the coupled effects in between the electromagnetic and the thermal. And just to give you an example, in a permanent magnet machine, of course, the permanent magnet characteristics themselves will vary with temperature. This will have an influence on the torque. It may have an influence in terms of the risk of demagnetization and so on. And of course, on top of it, we have the typical well-known dependency on the stator winding characteristics with temperature. So in a typical approach, one will have to do a multiple loop analysis, in which electromagnetic analysis will be performed. We'll establish losses at an assumed temperature. Then we will go do the thermal analysis. We will check to see if the temperature is as initially estimated, at least in the most important point. And if it's not, then we have to go back again, redo the electromagnetic, and so on. And we have to look a few times based, of course, on the experience and the goodness of the computational procedures and so forth. So when we design, then we have thousands of candidate designs on one side. We have multiple operating points, as in the driving cycle. The problem becomes extremely large, extremely large to start with. And one way to make it all possible, and the way we employed it, at least in this example, was to use a software that has coupled inside within the same structure both the electromagnetic and the thermal. This is MotorCAD, illustrated here. And MotorCAD uses for the electromagnetic an ultra-fast FEA, and for the thermal uses an equivalent thermal network. And we couple the two, and then it provides a cutting edge, because now we can analyze complex duty cycles. We can do all this in record time. And the software can be coupled in different ways. We illustrated that in other papers, where we have now efficiency maps, calculations. It may go to a different type of electromagnetic software, then come and do the thermal analysis and in MotorCAD. So going back to our Formula E example. Here we have a typical points on the driving cycles, and the ones that have been used at least in one iteration of the design optimization study to produce what is called a weighted loss, expressed here in per unit. So you can think of this as a measure of the losses that will influence the energy consumption and ultimately may affect the energy altogether, the electricity consumptions, batteries, and so on. On the other axis, we have the mass of the active mass of the motor. And as you can see, we have a big cloud here full of candidate designs, and then we can establish a Pareto. And of course, the problem is very complex, because we have to consider the system influences, other things that will be going behind the scenes, and so forth, and the thermal. So to summarize the main results on the machine that has been demonstrated, physically demonstrated, here we have listed the peak torque, continuous torque, maximum speed, power, the type of magnetic materials, at least at the high level, that has been used in the construction, and again, to bring acknowledgement. The manufacturer of the A motor is Equipmake, and the electromagnetic and the thermal design was done by Motor Design Limited, and we contribute the optimization. And speaking of the optimization, we'll have a technical paper that will come at the ECCE conference later this year, so that will be more in-depth coverage of the subject matter. Here are some drawings, some models of the Stator and Rotor. Important to note the Stator, the Rotor using spoke magnets, rare earth spoke magnets, high flux concentration. As we will go along and show some of the results, you will be able to see the magnitude of the magnetic loading. The Stator is a concentrated winding. This is an 18-slot, 16-pole combination with all the advantages that carries in terms of high winding harmonic factor and so forth. The windings are, of course, modular and concentrated. Cooling is ensured through a combination of air and liquid. And we also have axial sections shown into the motor, and here we have also shown the typical winding configuration. So the phases are grouped, red, yellow, blue in groups of 3. So take a look at the magnetic field and copper losses, and we have here a representation to scale of the magnetic flux density, extremely high values. So this is, you have to keep in mind, whenever we talk about this, the driving cycle is known. So if you have the tools in place to be able to handle such high electromagnetic loads, this is the way to go. The other takeaway from this slide would be the ratio in between the AC losses and DC losses in the winding. That's very important to monitor and optimize through the design. And then, of course, different combinations and solutions should be considered. Core losses, yeah. This is a highly loaded machine. Core losses, again, here we have a representation on the color scheme. We talk about substantial losses per kilogram. Yeah. I'll show later on what happens with the temperature as the car goes through the driving cycle. Now, in an IPM, of course, losses in the magnets will be substantially lower than in an SPM. But here we talk about a machine which has a high harmonic content in the MMF. It has a permeance variations, it has high frequency. So even the losses in the magnets can be of concern. We look at what the options are, and then we concentrated on the high energy magnets in order to have the high power density. And samarium cobalt, of course, holds an advantage in terms of temperature, resilience, and neodymium holds an advantage, at least at room temperature, in terms of resistivity as well as energy density. So common technique in order to minimize the losses in the magnets, which can be substantial, is to segment the magnets, even in an IPM construction. And then you have different options to try different combinations of both axial as well as cross-sectional segmentation. And one would do a parametric study to see which is the optimal number of segments to be employed. So once a design is completed, at least for machines that are expected to operate at what we label at the steady state, efficiency maps will be drawn. And this will be a thorough investigation of the torque versus speed space, where we look at what the efficiency values are. But for this particular application, even more important is the duty cycle. Yeah? Because we know, you remember, we know that driving cycle. So we have to do now the calculation of using the current profile and the expected speed and see what the torque is, what the losses are, and so forth. And we have to do this for a transient, basically, because it takes, here we have a representation of 20 laps. 20 laps, each with a drive cycle, and you could see it takes quite a few laps for the machine to get at its rated temperature. And by that time, you may need to stop for various reasons, then you restart, and so on. So the transient analysis becomes extremely important. Okay, so if we look at the experimental data, this is part of the demonstration. It shows good, fairly good response of the torque versus line current. Very important takeaway, of course, is the precision of the estimation as compared with the measurement. And then we have also measurements of the losses versus current. Again, satisfactory precision in that respect. And this brings to conclusion the first part of the presentation. The second part will give me an opportunity to talk about the emerging materials. And out of the many that may be out there, we'll focus on the carbon nanotubes, also abbreviated as CNT. And such materials have made the news in the last couple of years. And one of the reasons is because they hold a big promise of an extremely high conductivity. The carbon nanotubes themselves, before they are assembled systematically in a wire, they can have conductivity up to 100 megasiemens per meter. And if you look at what that compares with the copper, it's almost twice as high. The challenge is to make it at that kind of conductivity, because for now, by the time we assemble them in wire, we can maybe produce something in the range 2.4, which is orders of magnitude lower, and even for some of the most successful reported, it may be only at 10. So conductivity for a physical realized wire may be as low as 6 times than copper. But nevertheless, the density itself is also 6 times lower. So there opens up the opportunities, even with the materials as there are today, for some improvements. The other important takeaway is that carbon, the temperature coefficient of resistance is substantially lower than it is for the copper. So if the machine would be to operate at high temperature, if additionally we would find means of improved heat transfer, if we will do all this synergetic design of machine together with materials, the opportunity longer term, futuristic, may be out there. Now, our group works on an approach to enhance the conductivity by using plated copper into the wire. And we have at University of Kentucky, UK, as we call it, we have in the Fiber Development Laboratory at the Center of Advanced Energy Research, we have the largest spinning facility existing in the US academia. Simplistically explained, at one point you put in the carbon particles, and then you draw the wire or the fiber as it is, okay? And it is a complex process. Here we only get a glimpse of it. Now, copper plating to produce the wire introduces a further challenge. And my material scientist colleagues have put here together one schematic slide in which they try to compress as much information as possible. So one takeaway would be that at some point you need to not only to plate with the copper, but you also need to make sure that the copper is aligned in the right direction of the wire. Yes, the direction in which the current flows. So these are some of the manufacturing challenges at the research side. Now, from the electric machine world, we come at the problem and we try to establish at least a benchmark that would be realistic. If we would go and take the wire, let's say, and maybe we have seen cases like that, we take the wire and we make a drop-in replacement. I don't think that will be the best way to illustrate the technology, which is in its early days. So we focused our attention on a machine where copper losses are extremely important. In actual fact, they dominate the losses. And we ended up with a coreless topology, which opens further opportunities for improving also the heat transfer and the construction in between the nanocarbon tube windings and a simple supporting structure in the stator. So let's have a look at this construction. Before we do that, I should mention that this is inspired actually from work done years ago by my previous academic group at University of Bath, led by Professor Istam, and they built the high altitude aircraft, solar aircraft as it was, Helinet. They built the electric machines that power those aircraft. And what we see actually in the lower part of the slide is a representation of that old machine. Beautifully made, titanium frame, and then we have multiple discs of permanent magnet and windings. And the plan would be, and the design, which we did design studies, will be to take the nanocarbon wires, then we will assemble them into the coils. The coils get fixed into the stator. We have, with a multi-disc structure, we have the ability to increase the number of discs or to decrease them depending on the rating in order to make a feasible comparison. And then we will combine this with a rotor with permanent magnets, at least in one configuration. The last part of the last rotors would use a Halbach array, so there may not be even a need to have any kind of steel in the rotor altogether. So out of the many design studies that we have done, one is exemplified here, and we look at what happens as the speed increases, what happens in terms of performance as in power density, watts per kilogram. Now, you have to keep in mind the original machine was a so-called low-speed machine, somewhere here in the range of 1500 RPM. So at that kind of speed, in actual fact, the machines, in terms of watts per kilogram, they will be comparable. As the speed increases, if we consider the so-called CNT wire 2 and go back a few slides, this is the best case scenario, the one that had 10 mega Siemens per meter conductivity. We may find that that particular one has increased the power density twice as much as the copper. The other takeaway is that for those kind of machines, even the aluminum, in actual fact, may make an improvement above the copper. And there are reasons for that. One of the reasons could be related to the AC losses, the supplementary losses in a machine like this, which would be significant and will require the use of Litz wire and the like. In the nanocarbon tube construction, those losses are expected to be very small. By the very nature of the nano and the extremely small wire, plus the nature of the carbon, those are expected to be low and make an impact into the performance. The US Department of Energy takes great interest in the carbon nanowires. And they took a very radical approach because they looked at what happens in terms of the population of electric machines out there. And if you would be to plot the percentage of losses, the distribution of losses versus the motor rated power, and you do it for the low ratings at about, say, 1 horsepower, 2 horsepower, you'll see that the stator losses are really dominating the losses. So anything that can be done with this huge population of induction motors that we have into the even the most common applications would be beneficial. Yeah? So they set then very ambitious targets. The ambitious target will be first to produce a 28 American wire gauge. So this is American wire gauge. This is a very fine wire, by the way. It will be substantially smaller than we will use in a 1 horsepower machine, as the demonstrator is required in the second part of the project. But nevertheless, it would be significantly large in terms of the nano. So the first task would be to produce and demonstrate this 28 American wire gauge, do it consistently, at least on a 1 meter length, and then achieve at least a 33% reduction into the stator wire losses, in the I squared R losses. And you have to do that either per unit of weight or per unit of volume. And the comparison has to be done at 150 degrees Celsius, which works, of course, in the advantage of the nano to a certain extent. But you have to think of the challenges as well. Okay? And then once all this is completed, it has to be demonstrated. And the most challenging machine, those of us who are used with electric machinery would admit, I would think to that, the most challenging machine to beat is the single-phase fractional and a small horsepower machine, because that has been studied for a long time. It went through many, many design iterations. On top of it, on an induction machine, there are very intricate influences in between the magnetic field and the electric. So permeability is also very important. Copper losses are important from various aspects and so on. And then in order to make the demonstrator, of course, one would have to assemble everything in a realistic prototype. That will mean that we'll have to solve all the problem in making an electric insulation for the wire. We will have to make it compatible with the insulation systems and then assemble everything together. So in conclusion, things that we can do today. Good example coming from the Formula E for the more common application is that innovation with existing materials, things that really happens on a daily basis, can still be done. Great benefits can be achieved by employing automated design optimization, and very importantly, especially for machines that use duty cycles, or they can operate at high electromagnetic loadings, the ability to do analysis that will couple electromagnetic and thermal becomes important. And if we keep in mind that studies with the differential evolution will take thousands of candidate designs, the ability to do such analysis on a very quickly basis and satisfactory accuracy is of great importance. On a more distant future, lessons learned from the nanocarbon technology, it may be improvement coming from the materials, no doubt about it. But as we know from the conventional industry, it may take time to deploy such technologies. So personally, I would expect the first impact and benefits we will see is really in high-tech applications where the weight is extremely important and cost, of course, maybe not so much. And even those who would be able to deal with an increased size, physical size, but reduced weight, those would be maybe primary applications. Listed here, by the way, we'll make the slides available to those who are interested. Please keep in touch. And here we listed some of our recent papers on the topic, either joint papers on the coupling of electromagnetic or thermal or optimization, as well as two of the outcoming papers. One is on the design optimization of spoke type PM mergers for Formula E racing car. We will deal mostly with the equations behind the results that we have seen. And another one coming on the feasibility of the carbon nano tube windings for electrical machines with some of the case studies. We talked briefly about the solar airplanes, and on purpose I didn't want to include a figure of a solar airplane, a photograph, not to take away from the focus on the carbon nanotubes. But there are also the solar cars, and those who are interested, we have a team at University of Kentucky. This is big competition, at least it is in the US and also in Australia. I'm not so familiar with if it has any European counterpart. This is a team only with students, so the students will put together a car, and this is the one we have from Kentucky. It's also only powered by the photovoltaic installed on the car. And what makes it interesting from the electric machinery point of view, this type of machines are typically powered by axial flux machines, which are mounted inside the wheel itself. Yeah? So if we get to do the carbon nanotube axial flux, this may be one application in our courtyard. As a final remark, I would like to mention about there is this need, on one hand, to have better methods to design electrical machines, on the other hand, to bring up the new generations of engineers up to speed and train them. So what happened is two universities, as in University of Kentucky and Marquette University, together with one partner, merged design inspired by the legacy of the SPIT consortium, which many of you would be familiar, have established recently a consortium. And we have 4 inaugural members. It gives me great pleasure to thank them publicly for supporting the initiative. Grundfos, Kollmorgen, MTS, Regal Beloit. I should mention some of our sponsors are here in the audience today. And we look forward to welcoming other members as well. And also thanks go to our longtime supporter, ANSYS, who has been a great sponsor of the academic research. So thank you.